Hey CSE 101 students, Professor McDonnell here. In this short video, I'd like to give you a quick overview of computer science as a field. In the overview video about what this course is all about, I gave you a kind of a quick sense of it. I'd like to dig a little bit deeper, not too much deeper, but a little bit more into what this field is all about and the kinds of things we'll be thinking about this semester. So computer science, as I mentioned before, is about how do we use computers and other kinds of computing technologies, smartphones and things like this, to solve challenging problems in the real world. These could be challenges we face in the natural sciences, the social sciences, medicine, business, even in entertainment, and more fun aspects of life. How do we use computational thinking? How do we use problem solving to face these challenges, to overcome them? So computer science is very much an applied science. There is certainly a lot of theory in it, which we're not going to get into in the course. But all of that theory, I will tell you, has a goal of supporting applications. It's unusual to meet, in fact, a pure theoretician in computer scientists. Those people are known as mathematicians, really. So even those who you would point at that person and say, yes, that's a theoretical computer scientist, that individual almost certainly has some practical applications in mind. It's just the nature of the field, and I think part of what makes it, a valuable discipline of study in the human world, that we're in. What computer professionals do really is called computational thinking. It's this mindset. It's this kind of logical reasoning, almost like a puzzle-solving mentality that we have. When we're faced with some challenge. How are we going to solve it? It's like there's a certain urgency, like we just can't let that problem sit. We have to find some way to attack it. So you'll find that one of the typical sort of characteristics of a computing professional is problem solver. This person just can't let it go. We have to find a way to solve this problem. So think of this as the following. Computer science is essentially problem solving with computers. These solutions, more often than not, come in the form of algorithms. An algorithm and a logarithm are totally different. So an algorithm is an unambiguous, step-by-step procedure for solving a problem in a finite amount of time with a finite amount of resources. There's a lot of detail packed into that one short sentence. So it's unambiguous, meaning that every step is clearly articulated as clearly as possible. Keep in mind that these algorithms eventually are going to be turned into code, and computers cannot guess what you meant. You have to tell the computer exactly what you mean. So this is why algorithms, these procedures, have to be as clear as possible. The purpose of an algorithm is to solve a problem or accomplish some task, and that has to happen in a finite amount of time with a finite amount of resources. Let's look at that finite amount of time. Why is that an issue? Again, keeping in mind that the purpose of an algorithm is to solve a problem. Suppose I come to you with a set of steps and I say it's going to take forever, literally forever, to solve this problem. What does that mean? Well, I don't want to get too philosophical here with you, but think about that. It means that you're never going to really solve the problem. So therefore, the step-by-step procedure you gave cannot properly be called an algorithm. Likewise, an algorithm must not require more than a finite amount of resources. Resource is a very vague term here. Keep in mind again that algorithms are going to be implemented in code. They're going to require machinery to implement them. Well, there's no such thing as a computer with an infinitely large hard drive or an infinitely fast network connection. These things cannot exist in the real world. So any step-by-step procedure that says I need an infinite amount of storage space is not an algorithm by definition. Again, because of the practical limitations, the physical limitations of this universe we live in. So some examples of some examples of algorithms from the, let's say, everyday living, or from, I don't want to say the real world, because algorithms are real things, but examples of algorithms from everyday experience would be things like recipes, like baking recipes, or driving directions. assembly instructions, right? If you've ever had the misfortune of having to assemble a piece of furniture and the instructions weren't so clear, you probably weren't given an algorithm. You were given some approximation of an algorithm. Okay? But in all cases here, whether it's a recipe, a set of driving directions, or some assembly instructions, in each case, you have, hopefully, an unambiguous step-by-step procedure for accomplishing some task in a finite amount of time. Okay, so these are all algorithms for that reason. The best of these, of course, is a baking recipe. I like to bake, okay? And the best part of baking, of course, is that you get to eat your creation at the end. And hopefully you execute that algorithm correctly. Here's an example of a problem which is sort of typical of the kinds of things that budding computer scientists would face. And again, it's something that we encounter in the real world, which is putting a collection of things in some kind of order. So, if you take a deck of cards, for example, and we pick out, let's say, the ace through 8 of hearts, and these represent 1 through 8, we could come up with some procedure for putting these in order. And I suspect the procedure that you would derive would not be simply pick cards at random and put them in a random order until they're in ascending order, right? You would be a little bit more discerning there. You would use your logical reasoning to say, okay, do this step and then do that step and then do these other 100 steps perhaps, and you would have ace 2, 3, 4, 5, 6, 7, 8. And there are different ways of solving this problem, in fact, of putting these cards into order. Okay, and again, computer science majors in their first course, which would be like at Stony Brook, this would be CSE 114. They would study different algorithms for doing this. Okay, but in fact, you've already done these yourselves. Okay, anytime you take a stack of papers and you put them into, let's say, alphabetical order, or you take some playing cards and you sort them by suit, let's say. You're executing algorithms. You're designing and executing algorithms right there in the physical real world. Okay, so in this case, one algorithm might be to take the smallest card, let's say ace is the smallest, and put it at the front. Then find the next smallest card, the 2. Search through the deck. Oh, there's the 2. Put that towards the front, right behind the ace. Now let's find the 3 and put that near the front. Okay, that would be one algorithm for solving this problem. Keep repeatedly searching for the smallest card that we haven't considered yet and putting it towards the front. So this could be explained more succinctly and with less ambiguity, and you could actually specify an algorithm. You could write it out on paper, and then if you wanted, you could implement it in code if you liked. Okay, but the step-by-step procedure, deriving that procedure, is an example of computational thinking. This is the kind of things, kind of topics, okay, kind of problems that computing professionals think about. They sit back and they think. So really, computer science is largely a thinking person's game. Okay, we think of a programmer as a person who's like, tap, 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 tap on the keyboard all day long. Now, sometimes that is necessary, all right, and that's it can be a little bit of drudgery. I'm not gonna lie to you, okay. But what leads up to that is the fun part. Okay, is like figuring out, sitting back and thinking, how am I going to solve this problem? What do I need to do? What should I tell the computer to do to make this happen? There's the creativity. That's the creative part of this field. That's the fun part, is deriving those solutions, coming up with that algorithm. Then you go through the process of typing it up. Yes, that's true. Hopefully it doesn't take you too long. Okay? And then you can test your program. Did it work? And then when it works, it's great. You feel a little thrill. Oh, look at this. I spent an hour working on this thing, and my plan worked. You executed your plan, and wow, it works. Sometimes it's a surprise, like it actually worked. Okay, so you get a little bit of a rush when that happens. So over the course of the semester, we're going to be looking at what are called the 7 big ideas of computer science. This arrangement of topics actually comes from the Advanced Placement Computer Science Principles course. So I'm not teaching you APCS. This is not a high school class, obviously. Okay, but in fact, we're going to be touching on a lot of those topics. So over the course of the semester, I'll be talking about, and you'll be learning really, the creative aspects of CS. How we manage data information. How do we derive algorithms? How do we do programming? What role the internet plays in computer science, and what is the global impact of CS on the world. I'm going to spend a good chunk of time on that last topic actually. Again, each week I'm hoping to highlight at least one I would say worthwhile, and I don't want to say cool because that kind of trivializes it, but one like impactful application of computer science on the world, where CS is making a good impact on people's lives in a positive way. So often we think of computing as, oh yeah, I have this new cool app on my phone, or I just played this game on my PS5 or whatever. Yeah, computing is in there someplace. But how can we use computing to fight disease, to address poverty, to improve the lives of people, right? I don't want to sound melodramatic or silly, okay? But really, like, oh, I can change the world with CS. Well, to some extent, I guess, okay? But if we can have a little bit of a positive impact on the world in some area using our knowledge from CS, I think that's a good thing. You're contributing in a positive way to humanity. One topic here I skipped over deliberately is abstraction. So abstraction is an interesting idea. Usually when we hear the word abstract, we think about abstract art. So what's the purpose of abstract art? Okay, it's to push away the details and get to the heart of some concept, of some idea. That's essentially what abstraction is in computer science as well. These computers that you're using on a daily basis, your smartphones and game consoles and ATMs even, these are pretty sophisticated devices, in fact. They're very complicated. Way more complicated than the human mind can deal with. Abstraction, as it's applied in computer science, and in particularly in computer programming, is that, I don't need to know all those nasty details. I don't need to know, for example, how a combustion engine works or how fuel cells work to drive a car. I just turn that key, I hit the accelerator, and I go. All right? Likewise, when you're doing coding, you don't need to know all the nasty details of how the hardware works or how programming languages work. Why does Python as a language actually work? I type in commands and it works. You don't have to worry about that. That's the idea of abstraction. You abstract away, you ignore the nasty details and just focus on the big picture. Focus on what's important. That's the power of abstraction. This is a concept that I'm going to come back to over and over again in this course because it's one that we'll rely on a lot so that we don't get overwhelmed with detail. There's just so much technical detail and jargon and concepts, and oh my gosh, it just goes on and on. The good news is you don't need to know all of that or even most of it to be successful in CS. Otherwise, I would have given up on this field a long time ago. Okay, so in this course, you will be engaging your creative spirit a lot. Okay, while you're writing software, you'll be creating algorithms and implementing them in programs. As we go, I'll have to teach you a little bit about how the computer manages information and data. Different kinds of data need different kinds of treatment. The good news there is that the range of data types that we're going to be working with is not huge in this course. It's like big enough to be interesting, but small enough to be manageable. And again, all of these topics have the ultimate goal of solving problems that are important in the world. Again, we'll use abstraction to keep things manageable from a mental standpoint, quite literally. And we'll see, I would say, some of the exciting and really valuable contributions of computing to addressing some of the challenges in the world. Okay? But also some of the fun stuff too. Okay? It's not all serious. It's not all glum, okay, and dark stuff. Okay, but also some of the the fun things in life as well. Okay, so as again, it's like a little bit of a roadmap of what CS is about, what this course is about. And I think you'll find it, well, at least I hope you'll find it to be an interesting and worthwhile course during your time at Stony Brook.